Welcome everybody to the final session of this season of DOTS. Today we start with our Swati Gupta. Swati is an assistant professor and Fouts Family Early Career Professor in the H. Milton Stewart School of Industrial and Systems Engineering at Georgia Tech. She is the lead of ethical AI at the Multi-Institute NSF AI Institute on AI for Optimization, AI for Opt. She received a PhD from MIT in 2017 and a joint bachelor's and master's in computer science from IIT Delhi in 2011. Dr. Gupta's research interests are in optimization, machine learning, and algorithmic fairness. Her work spans various application domains, which I won't list, but she's also received many awards, including the JP Morgan Chase Early Career Faculty Award, and others that you can see in the, in the bio on our website. She has also been the prestigious Simon Berkeley Research Fellowship in 2017 to 2018, and she was selected there as the Microsoft Research Fellow in 2018. She received the Google Women in Engineering Award in India in 2011, and her research is partially funded by NSF and DARPA. Personally, I've known Swati for a long time. I remember back in the day when she was telling me that she couldn't get her head away from TSP, and I think that she still can't. It's one of those mind worms that will stick with you, and combinatorial structure just keeps coming back. And I think that's where we see her today, bringing her skills from ML into combinatorial optimization. So Swati, the floor is yours.
Thank you, Alex, for the very nice introduction. I guess TSP is now, I'm planning, okay, once I get tenured, then I can do TSP, but it's still a mind worm right there. Okay, so I'm really happy to talk to you all about reusing combinatorial structure for some machine learning applications. This is joint work with my students, Hassan Martari and Jay Mundra, who've been fantastic collaborators and have driven most of this work. This was published in Europe's 2021, so that's the archive link if you want to check it out. And in this work, I'm really, so the way I sort of explained, the way I'm thinking about it is it possible to speed up optimization problems that are combinatorial optimization problems by reusing some structure from previous solves? And so really, let's say I have a sorting algorithm and that's going from one set of permutations to another set of permutations. If I perturb the numbers a little bit, the same mapping really works and you don't have to resort these numbers again. And so we're going to bring this thinking into mirror descent framework. So first, I'm going to motivate these projection-based methods, which, online mirror descent is one example, but projected gradient descent, stochastic mirror descent, all of these are examples of projection-based methods in continuous optimization. We're going to look at these projections over combinatorial polytopes, which are known as submodular base polytopes. And then we're going to develop a toolkit that can reuse combinatorial structure. So a lot of these things are sort of toolkits. We have theorems on when these provably work, but a lot of the speed up that you'll see for reusing combinatorial structure will come in the experiments, which is the third part of my talk on modifying the Frank-Wolfe algorithm to make use of all of these structural properties and see how that speeds up in experiments. So we'll first start with online learning, and online learning is, something that's used by a lot of applications these days. A lot of algorithms around us, have this repeated framework where they make a decision, they have some historic data, they select an action or a decision, they incur some losses in a dynamic environment, and they go and update that decision. What's interesting for today's talk is a lot of these decisions that are taken at every time step, they need to be computed over and over again. And a lot of these algorithms really care about how do we perform well compared to the best fixed decision in hindsight. So there are two things to keep in mind here. One is the speed of making a decision, and the second is being able to learn to do well with respect to the best decision in hindsight. And this is formalized as what is known as regret. So, and I'll come to that in 2 slides. So these applications have, we might be learning matchings over pages and the rank in which they have to be displayed. We might be learning permutations of objects. So we might be learning over a permutahedron or the bipartite matching polytope, or we might be learning over shortest paths in a graph network. And this was some work we did on dynamic pricing of retail items that could be modeled as a shortest path problem. Or we could be thinking about spanning trees over an Intel chip, which needs to communicate and which needs to communicate through the least congested edges. And so the online framework here, what it'll do is it'll spit out a solution, which is probably going to be a convex combination of some solutions. It's going to observe, let's say pages are displayed at 1, 2, and 3, 4 ranks, observe what the user clicks are, and penalize items that were placed at a higher rank based on the amount of clicks. So all of this is just to say that the online learning framework over combinatorial objects is really nice. It lends itself to many applications. And the algorithms that can attain good regret guarantees. So good guarantees in the sense of converging to what the user likes, converging to a user preference that is fixed. So that's the regret benchmark. Online mirror descent is based on Zinkevich's adaptation on Nemirovsky and Yuden's algorithm 1983. And this is one of the, it's a seminal work of from 1983 of Nemirovsky and Yuden. And what it's doing is it's computing a projection step. So that's the a projection step. So an unconstrained gradient step followed by a projection at every iteration. Give me 1 second, actually. I'm not able to see my slides because of the videos. So, okay, how do I do that? All right. So please interrupt because I can't see the chat anymore. So please interrupt if there's a question. Okay, so online mirror descent is, so an algorithm that one can use for online learning over these combinatorial objects. And it involves taking an unconstrained gradient step followed by projection, potentially in every step of the algorithm. And the thing we are interested in using online mirror descent is because it optimizes the metric of performance, which is known as the regret, which is the performance based compared to the best fixed decision in hindsight. And it gets order optimal guarantee. So it's square root T regret that online mirror descent can achieve. But of course, these projections are a computational bottleneck. And this is not just there for online learning. Projection-based algorithms are pervasive in game theory, machine learning, stochastic, robust optimization. You put in stochasticity, you put in different kinds of projection functions, and so on. And that lends itself for use in many applications in many industries. And the attractive part about this class of algorithms is that they have order optimal guarantees or order optimal rates in various settings. But there is this computational bottleneck of computing projections, especially for polytopes that are combinatorially interesting. So the polytopes like permutahedron or spanning trees, these are the kind of polytopes with a large number of vertices that we want to optimize over. So just as one of our motivational examples for this work is online mirror descent versus online Frank-Wolfe. So Frank-Wolfe is this other class of methods that I'm going to mention in a few slides, which are not projection-based. So they don't move in the direction of the gradient to do that unconstrained gradient step, but they move approximately in the direction of the gradient. So they're always feasible. And what you see here on the slide is 2 experiments on the permutahedron, where there's really a gap in the regret over time that these algorithms can achieve. So online mirror descent variants can go to 0 regret. So they can get 1 over square root T convergence rate, average regret over time, whereas Frank-Wolfe variants can only get 1 over T to the 4th or T to the 3/4 regret over time. Right. And so there is a real gap in the performance of the algorithms. Of course, there's a trade-off in the computation time because online mirror descent is going to be very slow compared to Frank-Wolfe variants. So that's the main question of the talk. Can we speed up combinatorial computation of projections or problems within OMD? So online mirror descent, we are not going to care so much about this overarching method, except that we are computing projections of points that are perturbations of each other. And can we reuse the structure in that so that we can decrease this computational bottleneck of computing projections? So let me before we go into the toolkit itself, let me start building some structure of Euclidean projections over general polytopes, right? So if you look at a polytope and you look at this big circle on the left, then what you can see is that if I pick a point at random on this big circle, so big space around the polytope, I will most likely project onto the vertices of the polytope. That's where the most of the probability mass is. However, if I look at projections of points which are very close to a polytope, that's the second figure, then with high probability, I am avoiding the vertices and I'm actually very close to the same facets as my neighboring points are going to be projecting on. So with high probability, I'm hitting the similar tight inequalities in that projection. And this is something we can characterize, just looking at how much should the radius blow up so that my probability of hitting the same facets is at least 1 minus 1 over n. And so we see some dependence, which seems reasonable with respect to the perturbation, which is epsilon, and the radius at which I should grow more than the polytope. So keep these two pictures in mind. Right. So if I have online mirror descent that's walking all over the polytope, it's doing these gradient steps, it's getting projected back to the polytope, I should be able to recover some tight inequalities. If I was operating in some regime where I was really far away from the polytope, then I should be projecting back to the vertices. All right. So let's get into the toolkit and let me set up the problem more mathematically. So we are going to look at submodular based polytopes, which are polytopes such as the convex hull of permutations. And these polytopes are interesting because projections are really hard. These polytopes are defined by an exponential set of constraints, which bound the total weight of a subset of elements. It bounds that the total weight has to be at most the submodular function value. These functions f have properties that are called diminishing returns. And the way this polytope is defined, it uses an exponential number of constraints. The base polytope that we are interested in is basically a facet of the submodular polytope, where I'm basically looking at all convex hull of permutations. So this lends itself to many interesting objects, such as also convex hull of spanning trees. And as we change the submodular function, we can get to different applications in machine learning. For example, structured regression with submodular penalties for background subtraction, sparse PCA, and so on. So you can change the submodular function and you can get to different combinatorial properties. So we're going to be projecting on these polytopes. And the algorithms for computing projections on these can be basically classified into 3 different types. So one is a set of algorithms, which I'm calling combinatorial algorithms. So this was, for instance, a part of my thesis work with Michelle and Patrick, which we called infix, which composes of specified movements in the polytope. So order n movements inside the submodular polytope with very specific directions, and you compute the maximal movement. And this computes the exact convex minimizer for a separable function modulo solving a univariate equation. And so these approaches are, for instance, also they were explored by Cronenwald in 91, by Nagano et al. In 2011. So these are structured movements. They're using combinatorial properties, but they're expensive because they use what is known as a submodular function minimization. Okay. The projection-based methods, not really applicable for computing projections. It's a cyclic problem, right? These projection-based methods like online mirror descent, as we saw earlier, needs to compute a projection. We don't have that. We actually want to compute a projection. And so the other class of methods is the Frank-Wolfe or conditional gradient variants. And so what does that do? What do these methods do? They start with a point where we know that the point is feasible. They look at the gradient, They look at the gradient of that point. So they look at the gradient at xt. They maximize a vertex that mimics the dot product. So the maximum dot product with the gradient, with the negative of the gradient. So that's this vertex vt, which is called the Frank-Wolfe vertex. And they move towards that. So because they're moving towards a point that's already in the polytope, these methods always guarantee feasibility, which is fantastic for submodular polytopes. We get around solving submodular function minimizations. They look at the active set, which is what the convex hull is, which is how xt was represented in. And as they compute xt plus 1, they update that active set. So this, just using movements towards Frank-Wolfe vertices, gives a 1 over t convergence rate for Frank-Wolfe, vanilla Frank-Wolfe over polytopes. But if we also include away step vertices, so we are including more directions, then these can avoid cycling and give us a linear convergence rate for smooth and strongly convex function, as we would expect in a projection-based method. Of course, this does not lend itself to every generalization or every general framework in which projections can be considered. And this is why we see that rate disparity between online Frank-Wolfe and online mirror descent. Okay. So this gets us to the toolkit. For some background for the toolkit for now reusing combinatorial structure. So what is it that I want you to keep in mind? Keep in mind an overarching method like mirror descent or projected gradient descent, where you have these sequence of points that you want to project onto the polytope. You have some information from previous points. Our polytopes are submodular polytopes, and I'm going to present results for Euclidean distances. Okay. So the first tool is what we call infer, which is given yt that is projected to xt. If I give you a perturbation yi, can you find some tight cuts that xi should also satisfy? So that will help us in computing the projection of yi. So to answer this, we go back to first principles and we look at the KKT conditions. We look at the first order optimality conditions that a minimizer should satisfy when we minimize a convex function over a constraint set. So what are the first order optimality conditions? That if I look at the negative of the gradient, I should not be able to walk in that, or I should be the dot product with the negative gradient, and the difference of any 2 points in the polytope should be greater than or equal to 0 for all points in the base polytope or any other polytope. So this is independent of this being a base polytope. So we look at what the first order optimality should be. And the way I parse the first order optimality is really that if I look at the gradient of the current point, then, and I look at things that minimize that gradient as a linear cost function, then the current point should also be one of the minimizers. So that's the bottom inequality here. So look at the gradient at x star. If x star is a minimizer of the gradient as a linear cost function, then x star is a minimizer of the original convex function. And this, I think, is a really nice way of thinking about first order optimality, because now I can start getting in my combinatorial properties into the problem. So in particular, right, so this acts as a certificate of optimality, right? So if I have a point x star and I want to check whether this is a minimizer of my function, I can compute the gradient and check if it's a minimizer of that gradient as a linear cost function. Good. All right. So the first order optimality in a submodular polytope reduces to checking the following property. So look at the gradients of every edge for a separable convex function. Look at, so I'm looking at the elements of my base polytope, and I'm ordering the partial derivatives based on their partial derivative value. So I've ordered my elements. So E1 has a lower partial derivative than E5. E5 has a lower partial derivative than E3, E4, and so on. Okay. And once I look at these, the ordering of the elements basically allows me to read off tight cuts that if this point was a minimizer, it should have satisfied. So the topmost tight cut is f of E is equal to x of E. So remember, the submodular polytope bounded the amount that any subset of elements could be raised to. That was the bound. So this is now a tight inequality where x over E, x over all elements summed up has to be equal to f of E. The next inequality is basically because of the bottom, all except the top one. So f of E minus E2 has to be tight also. The next two, and the last one. So there is a very nice reason for why this happens. So why does first order optimality actually translate to this property in the gradient space? Is because for submodular polytopes, Edmonds' greedy algorithm gives you the optimal, the linear minimizer for a cost function, for a linear cost function, right? And what does Edmonds' greedy algorithm say? It says that the lowest cost, I'm going to increase it as much as possible. And so what's happening here is the lowest cost is that of E1 because of the gradient space. The lowest cost, I'm going to increase E1 as much as possible, but E1 can only be increased to F of E1 because of the submodular polytope. If I look at the lowest two costs, then that comes from the greedy algorithm. If I look at the lowest two costs, then I should be able to increase those as much as possible. And so that gives me the second inequality. So the structure, the equivalence of first order optimality and this structure in the gradient space really comes because of Edmonds' greedy algorithm being optimal linear optimization oracle over the submodular polytope. Okay. But if you've not seen that before, for the purposes of this talk, if I look at the gradient space and the gradients are well separated, I can read off my inequalities. That's the key idea. So that gives us our first infer toolkit, because even if there is some perturbation of values, if they've not settled to the right amount in a projection algorithm, I can read off these inequalities and I can infer that, xi is has to be close to xt because yi is close to yt. And so xi's gradient cannot be that far away from xt's partial derivatives. And that allows me to infer some of the cuts that xi must provably share with xt. So that's the first toolkit. That's the first part, which is infer. If projected points are close, then projections are close. And information on the partial order derivatives help us derive cuts for the next point xi. The second thing we can do is that we can use this within Frank-Wolfe, within a conditional gradient algorithm. So as I continue projecting, so conditional gradient algorithms will work by taking tiny steps based on the gradient, and they will go towards the optimal solution, right? Like, so as I move in my trajectory for conditional gradient and I get towards xt, I can bound the distance towards the unknown optimum, right, in that projection subroutine. And so as I know the distance, I know how much the gradients, the partial derivatives can now change, and I can start already inferring tight sets from that using that first order equivalence, first order optimality equivalence. Okay. All right. So the next toolkit is thinking about Frank-Wolfe variance. If I really used projection if I really computed the previous projection in online mirror descent using Frank-Wolfe, then I could use this active set of vertices in which the previous projection lied, and I could just start my Frank-Wolfe algorithm from that. So that's reuse. I think this is not a new idea. It's been done in many papers, but we also bring that in as, this is one of the tools we are going to use. But this is definitely not a new idea. And the next tool I think is interesting is a restrict tool. So this is something that conditional gradient algorithms have not been able to do, because even if they hit a tight face, even if they hit a facet while the convex optimization is going on, they will most often leave that tight inequality and go back to the interior of the polytope. But because of our infer tool, where we can provably find tight inequalities, we can actually start restricting a problem. We can narrow it down, we can restrict, we can fix some constraints like in fix, and we never need to leave those constraints again. So what restrict does is, once we've fixed these tight constraints in this example that you see on the right, once we fix this cream face, then we restrict our linear optimization oracle only on that face. And what that allows us to do is get a better angle in the Frank-Wolfe vertex. So now when I want to approximate the gradient, which is minus grad of h for zt, when I want to approximate it, if I approximate it over the entire polytope, so I'm doing linear optimization over the entire polytope, which gets me to VT, but by restricting to this cream face, I can get it to WT. So I get a better approximation of the gradient by restricting to tight inequalities. And I can restrict to tight inequalities because I know they are provably tight because of first order optimality conditions. Okay. The next thing we do is, I would say maybe a little bit heuristic-y, but something that really works, is that once we detect a tight inequality, we need to check whether this is the entire set of tight inequalities or did we miss something. So we run a what if optimization where we say, what if this was a set of tight cuts? So here that's the cream inequality, and we just minimize the convex function over that, which is an easier problem than minimizing over the entire submodular polytope, which has an exponential number of constraints. And so that acts as a check for knowing whether we've actually found all of the tight constraints or if there is some other tight constraint to be found. And with that, we can also round to a nearby point because of the discretization, or because of the structure of submodular convex minimizer over submodular polytopes for nice enough functions like the Euclidean projection. So with all of these ideas together, we change the way conditional gradient algorithms operate. And we call this an adaptive away step Frank-Wolfe method. So what we do is we use infer. We can, as we get closer to the optimal solution, we infer more tight sets. We check if we found the optimal solution by relaxing and solving that problem. We restrict to the tight constraints that we found. We change the linear optimization from greedy to be restricted to that phase. We use away step Frank-Wolfe as is with all of this information that we have, and we reuse this information in the subsequent projections. So with all of these modifications, what we can show is we can still maintain a linear convergence rate. And if the minimizer of the convex function is on a facet of the polytope, so it's on the boundary, it's not in the relative, it's not in the interior, then we can improve the convergence rate because the pyramidal width constant improves. So the rate improves if the optimal solution lies on a lower dimensional face of the polytope. So we can show that mathematically. And in practice, this is fantastic because, first of all, we can recover through our theorems, we can provably recover. We see that a lot of tight sets are used when you project points that are close by. We can recover most of them, that's the blue curve, and we can recover most of them through theorem 5, through the infer tool, which is a theorem in our work. The next experiment is really exciting because remember one of the first motivation slides that I showed you, we had difference in the regret between online mirror descent and online Frank-Wolfe. And what we can see here is that we can decrease the runtime of mirror descent variance by using our away squared Frank-Wolfe. So if you see in the first plot, this is a 2 orders of magnitude difference in the runtime by using away squared, adaptive away squared, away Frank-Wolfe, a squared Frank-Wolfe. So it's a 2 order of magnitude difference in the runtimes if you use all of the tools that I mentioned. And this difference is also significant if we change the where the projection is actually placed. So where the regret benchmark is placed in the online mirror descent framework. So this is running online mirror descent. So think of these experiments as running a recommendation system where either I have a complicated preference or I have a simpler preference of all my customer base. And when I do this, I'm able to run online mirror descent variant with 2 orders of magnitude improvement in runtime. Of course, this is still slower than online Frank-Wolfe. So, but we are at least bridging the gap and bridging the gap significantly between these. So that's the end of my talk. Thank you for your attention, and I'm happy to take questions, but probably I'm out of time. So in the breakout sessions then.
Thank you, Swati. Yes, I think that maybe in the interest of time, we will maybe keep the questions for the breakout rooms, which will happen after Emma's talk. But I really appreciate the really nice talk, and I'll come at you with some questions at the breakout room.
Thanks, Alex. Yeah.
Okay, great.